Lesson: Theoretical Frameworks for AI-Driven Threat Hunting. Theoretical frameworks for AI-driven threat hunting are essential for enhancing cybersecurity. These frameworks provide the foundation for developing systems that actively seek out and identify potential threats to an organization's digital infrastructure. By leveraging machine learning algorithms, predictive analytics, and advanced data processing techniques, AI-driven threat hunting can transform the way cybersecurity professionals detect and respond to cyber threats. One of the primary theoretical frameworks underpinning AI-driven threat hunting is machine learning. Machine learning involves training algorithms on large datasets to recognize patterns and make predictions based on new data. In the context of threat hunting, ML algorithms can be trained on historical cyber attack data to identify the characteristics of malicious activity. For example, supervised learning techniques can be employed where labeled datasets of known threats are used to train the model. Once trained, the model can then classify new data and identify potential threats based on the patterns it has learned. Another critical theoretical framework is anomaly detection. This approach involves identifying deviations from established norms within a dataset. In cybersecurity, anomaly detection can be particularly effective in recognizing unusual behavior that may indicate a security breach. For instance, if a particular user account suddenly exhibits activity that is significantly different from its usual behavior, this could be a sign of account compromise. Anomaly detection can be implemented using various techniques, including statistical methods, clustering algorithms, and neural networks. These methods help in identifying outliers in the data that could signify potential threats. Deep learning, a subset of machine learning, also plays a crucial role in AI-driven threat hunting. Deep learning algorithms, such as convolutional neural networks and recurrent neural networks, are capable of processing vast amounts of data and identifying complex patterns that traditional algorithms might miss. These algorithms can be particularly useful in analyzing network traffic, user behavior, and other high-dimensional data sources in real time. For example, RNNs can be used to model sequences of events, such as login attempts or file accesses, to detect anomalies that may indicate a security threat. Natural language processing is another theoretical framework that can enhance AI-driven threat hunting. NLP techniques enable systems to understand and analyze human language, which can be invaluable in monitoring communications for signs of potential threats. For instance, NLP can be used to analyze emails, chat logs, and social media posts for keywords and phrases that may indicate malicious intent. This capability allows organizations to proactively identify threats based on the language used by potential attackers. The integration of these theoretical frameworks is further supported by the use of big data analytics. Cybersecurity generates massive amounts of data, and the ability to process and analyze this data in real time is crucial for effective threat hunting. Big data analytics involves the use of advanced data processing techniques to handle large volumes of data, enabling the identification of patterns and correlations that may not be apparent in smaller datasets. This capability is essential for detecting sophisticated threats that may be hidden within vast amounts of benign activity. To illustrate the effectiveness of these frameworks, consider the case of a financial institution that implemented an AI-driven threat hunting system. By leveraging machine learning and anomaly detection techniques, the system was able to identify a series of unusual transactions that were indicative of a coordinated cyber attack. The system flagged the transactions for further investigation, allowing the institution to respond quickly and mitigate the threat before significant damage occurred. This example demonstrates the potential of AI-driven threat hunting to enhance the security posture of organizations by enabling proactive threat detection and response. In addition to these theoretical frameworks, it is important to consider the ethical implications of AI-driven threat hunting. The use of AI in cybersecurity raises concerns about privacy, bias, and accountability. For instance, the data used to train machine learning models may contain biases that could lead to unfair or discriminatory outcomes. It is essential to implement measures to mitigate these risks, such as using diverse and representative datasets, implementing fairness-aware algorithms, and establishing clear governance and accountability structures. In conclusion, the theoretical frameworks for AI-driven threat hunting provide a robust foundation for enhancing cybersecurity. By leveraging machine learning, anomaly detection, deep learning, natural language processing, and big data analytics, organizations can develop sophisticated systems that proactively identify and respond to potential threats. These frameworks not only improve the effectiveness of threat detection, but also enable organizations to stay ahead of emerging threats in an increasingly complex cyber landscape. However, it is crucial to address the ethical considerations associated with the use of AI in cybersecurity to ensure that these technologies are deployed responsibly and fairly. By integrating these theoretical frameworks with ethical best practices, organizations can achieve a higher level of security while maintaining trust and accountability.